Everyone, let me share. Am I audible? Yes, no. Hello, am I audible?
Yeah.
Okay, I'm going to share my screen now. Just hold on a second. Um, you should be able to see my screen, right?
Yes, sir.
Okay, so just a reminder that NPTEL is conducting mock tests every Sunday. Did this happen today also?
Yes, it happened, sir. But I don't know if all the answers are given correct.
Okay, that's a different thing. It's fine. Answer key that can be debated. That's fine. Let's see. So anyway, I strongly encourage you to attend these. So last time I remember there was some problem, people were not able to get in, so I don't know whether this problem persisted or not. Let's see. We'll give the feedback, you guys provide the feedback. Anyways, let me begin. This is Gate Physics live sessions. My name is Amit. I'm a PhD scholar at Indian Institute of Science, Bengaluru. This is week 7. Today is January 8, 2023. Right. Just as I talked in the last session, and you might also have seen on the website that for the next 3 sessions we'll be doing electronics part. Today is dedicated to digital electronics, so I'll quickly do. How should I put it? Quickly revise all the relevant things, and then we can jump into solving the problems. These are fairly straightforward problems. Digital electronics is highly scoring because the questions that can be created, the number of concepts are fairly limited. So if you understand the basics, you can score in these type of in these questions. So let me begin. So first, the basic thing is the number systems. So these are different number systems that we encounter, that we see in our daily lives. So decimal is we are habitual of seeing. Symbols are 0 to 9, and the base is 10. The most brilliant feature is that it's human. We have evolved to see this around us from our childhood. The second number system is binary. This is very good for computers, which recognize only two symbols, 0 and 1, on or off. So 0 and 1, the base hence is 2. The base denotes the number of symbols, you can say. And it's the characteristic feature is that it's the simplest. There is no there's no scope for confusion. It's either on or off. There are no middle states. Now the problem is that so when we go to the higher numbers, let's say if you want to express like millions, let's say you want to express 1 lakh, right? If you try to express in binary, it will take a huge amount of space. So what computer scientists determined that we need a different mechanism so that to compress this. So what they did, they identified is the hexadecimal as one. So it has base 16 and naturally 16 symbols. 16 symbols are 0 to 9, the decimal symbols that we know, and the capital A to capital F, the English alphabets capital A to capital F. The good thing is that what the objective of hexadecimal is to compress the binary. So it has compressed. And another number system which we fairly see is the octal number system. The base is 8, the octal comes from the number 8, and naturally the symbols are 0 to 7. So its benefit lies somewhere in between, that it does not compress that much. So that's the, depending on the usage, we use different number systems, right? From an exam perspective, the key thing to note, how to convert one number system to another. So you must know this, because these are fairly how should I say this, standard practices that I'm saying here. For convert any given number to decimal form, you just convert to requisite number system using LCM. So for instance, let's say, by the way, the numbers are denoted like this. So for instance, it's 14 in base 10, right? So this will be given as this is E in base 16. So that's how they're denoted, brackets, and the base is on this side. So if you want to convert from any number system to any other, let's say we want to find what is this in binary, right? So it's simple to do. First you convert the whatever numbers you have to decimal form, right? And then you can use the LCM trick to find the number in the binary form or any other number system, right? But there's a trick, there's a shortcut, because I told you hexadecimal was evolved so that we can compress binary. So there's a trick that when you want to convert from binary to, you are given binary, you want hexadecimal. So 4 numbers of binary will mean one symbol of hexadecimal. For instance, let's say it's written let's say 7 in decimal is written as 0111 in binary, while it's written as 7 in hexadecimal itself, right? Another example is that 12 in decimal it will be written as 810, sorry, 1100 in binary, and this can simply be written as so 12 is ABC, right? 10, 11, 12, yeah, C in 16. So four symbols in hexadecimal, four symbols in binary correspond to one symbol in hexadecimal. So if you are given, let's say, F1 in hexadecimal, that would mean 1111. This is the first term for corresponding to F, and the second term would be 0001. This would be corresponding to the 1. So this is in binary. This is a useful trick. Sometimes the problems ask these things, so it's I'm just writing it here for the sake of completion. Okay, right. So let me move forward now. Similarly, to convert binary to octal, the three symbols of binary is equal to one symbol of octal. Right, but the crux of this lecture, the session, would be focusing on Boolean algebra and logic gates. So what is a Boolean algebra? In Boolean algebra, we have three primary operations. First is the conjunction, which is often denoted by a multiply symbol, or multiply symbol. Disjunction is denoted by the plus symbol, and negation is denoted by either the tilde or bar. So they're different symbols. Conjunction means, you can simply see, it's the AND gate sort of thing. Disjunction is the OR gate, hence the symbol plus. Negation is inversion. If it's 0, it becomes 1, 1 becomes 0. Coming to 1 and 0, there are only two values which we use in Boolean algebra, that is 0 and 1. These are only two values, and these are the operations that we can play around over these numbers, right? And there are some couple of laws which we use to our advantage to simplify the Boolean expressions, right? So these are called De Morgan's laws. So on the left you have the conjunction node, the dot is there, so this means the conjunction. If you want to convert a conjunction to a disjunction, you can use it by using this formula, and correspondingly, if you want to convert a disjunction, note the plus here, into a conjunction, note the dot here, you can use the second De Morgan's law to your advantage. It's when you practice, then you tend to understand what we are talking about here, but I have just simply noted this down so that in just a single slide you can have something to refer to, right? And based on these so based on these primary operations, conjunction, disjunction, and negation, we can create gates. These are called logic gates. They perform some logic. So for instance, you can look at the NOT gate. NOT gate simply performs, this is the symbol, by the way, A and bar. Sorry, this is the expression, this is the symbol, circle, a triangle followed by a circle. Similarly, this is the conjunction that I talked about, conjunction, and this is the disjunction, right? And there are some other gates like NAND, NOR, and so on, right? So we'll talk about NOT, AND, and OR in a little bit detail, but let's just only focus for the time being on NAND and NOR. So NAND, you can see, is AB whole bar. This means you take a conjunction and then the negation, and the truth table is essentially just the list of all. You try to find out the output corresponding to all the possible inputs. So there are two inputs here, A and B. So I have 0, 0, 0, 1, 1, 0, 1, 1. That is the possible combination of inputs, and you can find the value of x as A times B whole bar. 0 times 0 is 0, and if you take a bar, it will come out to be 1. So correspondingly, this is a truth table, and this is a very powerful tool. Just if you know the algebraic expression and the truth table, you can virtually solve any problem from at least the logic gates, right? And NAND and NOR have a speciality. Can anyone tell me why NAND and NOR are special gates? What's the speciality? Can anyone point me?
Yes, we can.
Go ahead, one by one.
Like another gate, like AND or.
Okay, yeah, correct, Harish. Someone else was also speaking. Go ahead now. I heard two voices. So one is Harish. I think he has spoken it. Okay, Harish is correct. So what we can do? Excuse me. Yeah.
It is also known as a universal gate.
Yeah, very good. That's thing is coming too. So what you can do using the NAND and NOR. See, I told you there are three primary operations: conjunction, this is dot, second is addition, and the third is negation. So if any gate is able to perform these three transformations just by using their own flavor, so let's say you can use 4 NAND gates to, let's say, perform an OR gate, it's fine, you are using only NAND gates. This simplifies a lot when we practically apply them, because these NAND gates are on ICs, integrated chips, right? So ICs, so they are integrated circuits, sorry. So there it's easy if you can buy only NAND ICs, right? It becomes very easy. That's a very powerful tool. So we'll see in the next slide. So here is why is called a NAND gate. You can convert any gate You can create any gate just by using NAND gates. So this is the NAND gate, you can see this is the symbol. So here Q would be AB whole bar. You can see it's a NOT gate here, right? So why it's a NOT gate? So I'll write the truth table here, AB, and then the output is output is this, right? So there is only one input, right? So either A is 0, A is 0, B will also be 0 because they are shorted. If A is 1, B is 1, and we know the output is AB whole bar, right? So 0 into 0 bar, this will be 1, and 1 times 1 bar, this will be 0. So you can see when the input is 0, the output is 1. When the input is 1, the output is 0. This is nothing but a NOT gate or an inverter. Hence, this configuration is also NAND gate. Just by using one NAND gate, you can create a NOT gate also, correct? Similarly, now look at this on the left from the second this feature on your screens. So this output will be AB whole bar, but if you then you put a NOT gate in front of it. Note this is a NOT gate. Then you get an AND gate. Similarly, you can get all the other configurations in this slide. You can see I'm not going to go through all of them, but my point here is to establish that just by using a NAND gate, just by using one NAND gate, you created a NOT gate. By using two NAND gates, you can create an AND gate. By using three NAND gates, you can create an OR gate, and so on and so forth. The rest you can look up. Similarly, you can do with NOR gate also, right? So I'll again do one example of a NOR gate. So just to emphasize what I'm talking about here. So this we have NOR gate. So let's talk about this example. So here only the NOT gate first. So the two inputs are A and B, and the output naturally is Y equal to A plus B whole bar. That's how it's denoted. So the input can be 0 and 1. A and B are both the same, so this has to be 0 and 1. And so let's try A plus B whole bar. So 0 plus 0 whole bar, this will be 0 bar, this will be 1. 1 plus 1 whole bar, this will be 1 bar, this is 0. So we notice that when the input is 0, the output is 1. When the input is 1, the output is 0. This is the characteristic of a NOT gate. So again we see that just by using one NOR gate, we can create a NOT gate. And similarly, you can see other configurations also. So because sometimes in the past, the direct questions have been asked that in order to create a NAND gate, how many NOR gates do you use? So questions like that. So it's good that if you know how to create these. How to create this, I will not solve a question today, because I solved two such questions in my previous session, the last few months ago, which I took. If you are interested, you can look through that. But just I wanted to touch base that this is an important question regarding universal gates, right? So just as for the people who came late, this is a mock. NPTEL is running mock tests. I just wanted to emphasize it again. You're requested to, if you are interested, you're requested to register every Sunday 2 to 5 p.m. Right. So so now I'm done with the theory, more or less done with the theory part. Now we'll jump into solving the problems. Okay, so I'll pause a bit over here. If you have any comments or questions, please feel free to ask, because now we'll be solving the questions based on the theory that we had developed. So I'll pause a bit over here, and if there are no comments or questions, we'll move forward and see how to approach and solve these problems. All right, I mentioned
D is right. D is right option.
Okay, it's good, but we are more interested. The goal here of this class is I mean, how should I say this? Is just to define the approaches. So that's what I'm going to do. I'll approach it from a very simple standpoint, and you are obviously welcome to devise your own approaches. I'm here to just to demonstrate how I approach the problems. Okay, so if there are no comments or questions, what I'll do is that by the way, I've shared my email ID and my YouTube channel link just now. So I told you that you can go through my previous videos on digital electronics if you are interested, where I talk about universal gates and some other problems. But this lecture is standalone. So let's go ahead. So this is the problem from 2010. Now what I'm going to do, I've created a video on this solution. I'm going to play the video now. Okay. So you should were you able to hear the audio? Sorry, the video?
Yeah. Yes, sir.
Okay. So I'm going to play it again. Just excuse me for a second. The problem statement from Gate Physics 2010 reads as follows. For any set of inputs A and B, the following circuits give the same output Q except one. Which one is it? So here we have been given 4 combinatorial circuits, and the question says the output of 3 of them is the same and the output of one is different, and we need to find the circuit which has the different output. This is a multiple choice question with only one correct answer, and we'll try to find the correct one. Since this question is based on logic gates, let's have a quick overview of the logic gates first. So in the top row of the table, you can see the name of these logic gates like NOT, NAND, OR, and so on. Just below that is the algebraic expression. Note this bar denotes negation. Negation means, I will see in a bit what negation means. Then this is what is called the conjunction. You can see there is a dot here. This is also known as conjunction. This thing is also known as conjunction. On the other hand, this plus symbol is also known as disjunction. So in logic, in mathematical logic, conjunction and disjunction are like just excuse me, someone wanted to join. I'll resume playing the video. Are in turn defined in more depth by something called a truth table. So for simpler understanding of the truth table, you list all the possible combination of inputs. So for instance, let's just take NOT gate. By the way, this is also known as negation. Negation means we are negating it, or sometimes this is also known as inverter. So there is only one input. So NOT gate says if the input is 0, the output will be 1. If the input is 1, the output is 0. Hence negation or inversion, right? So a truth table lists, you first list all the possible combination of inputs, and then you list the outputs. That's what the truth table shows. Now let's look at this AND gate, which implements the conjunction. So here there are 2 inputs, you can see A and B. So A and B are like this, and the 4 possible combinations are 0, 0, 0, 1, 1, 0, and 1, 1. And the output is defined in such a way, by the way, this is the symbol for AND gate. Output is defined in such a way that the output, you find the output using this formula, A dot B. So 0 dot 0, 0 dot 0 will be 0. 0 dot 1, dot means multiply. So 0 times 1 is 0. Then it's 1 times 0, that will again be 0. And finally 1 times 1, it will be 1. So you can see the output will be 0, 0, 0, and finally 1. Now let's come to this OR gate, which is called the disjunction. It's denoted by the algebraic expression A plus B. This is the symbol for an OR gate. So again the inputs are 0, 0, 0, 1, 1, 0, 1, 1. And when we try to find the output, we just put a plus sign between the inputs. So 0 plus 0 will be 0, 0 plus 1 will be 1, 1 plus 0 is 1, 1 plus 1 in Boolean algebra, in 1 bits, it will be 1. This means high or high will be high. Finally, let's have a look at this XOR gate. This is also known as exclusive OR. And this is the way it expressed. The alternate way of expressing it is A B bar plus A bar B, where bar is the negation. So if you try to evaluate A B bar plus A bar B, so it will be, first term will be 0 times 0 bar plus A bar, 0 bar times 0. So it will be 0 times 1 plus 1 times 0, it will be 0. Let's do the second term also. So it will be A B bar. So A is 1 dot 0 bar plus A bar B. So 1 bar dot 0. This will be 1 dot 1 plus 0 dot 0. This will come out to be 1. Similarly, you can evaluate the other two things. So by the way, this is the truth table for XOR, right? So again, truth table is nothing but you try to find the output based on the algebraic expression for all set of inputs, right? So now let's get back to the question. So this was the first, we were given 4 circuits. This is the first circuit, right? So let's just first try to evaluate what will be the output at this node. Now note that this is an XOR gate, right? So I can write the output here as AB bar plus A bar B, right? Let's try to find the output at this node now. So this node is nothing but negation of B, node B, and then so this will be B bar. Now thirdly, we have this AND gate. So AND gate would be, so I can write this node Q. So I am writing it here. So Q will be equal to the first input, which is AB bar plus A bar B times the second input, which is B bar. Straightforward. Now we simply multiplied it. So it will be A B bar times B bar plus A bar B bar. Now we know B bar dot B bar is nothing but B bar. So this is A B bar. These are rules of Boolean algebra. For instance, let's do this. So let's say there is some value y, okay, and so let's say it can have 0 or 1, and let's say there's some output z equal to y dot y, okay. So it will be 0 dot 0 will be 0 and 1 dot 1 will be 1. So y square will be nothing but y. So here again you can y is b bar, so one of the b bar gets dropped, so it will be a b bar and b dot b bar. So let's again try to find the output. Let's say y again is 0 and 1, and let's say x is y times y bar. Okay, let's try to evaluate the value of x. So it will be 0 times 0 bar, it will be 0 times 1 will be 0, and then it will be 1 times 1 bar, this means 1 dot 0 equal to 0. So when you multiply the a term and its inversion, its negation, the output will always be 0. So hence this term will drop out, so we'll get q equal to ab bar. So now we have solved the first circuit. This is the second circuit. So let's first try to evaluate the value here. This is just the potential at this node will be nothing but b bar, and finally this is an AND gate, so q will be equal to the first input, which in this case is a, so a times the second input, which is b bar. So again we evaluate the output is a b bar. Let's go to the third circuit. So first we evaluate this the node, the output the voltage here. So this is nothing but negation of b, so this will be b bar. Now let's try to evaluate the potential here, the value here outside the output of this AND gate. So the output of this AND gate would be the first input, which is a, times second input, which is b bar. So the out value here would be a times b bar. Now let's try to evaluate this orange circle. So one of the inputs is b bar, you can see here, and the other input is a. Note this is the wire, so a, and this is again an AND gate. So the output here at this node would be a times b bar, the first input times second input. Now let's try to evaluate the output at the output of this green, the AND gate shown in green. So AND gate will be the first input, which is a b bar, times second input. Second input is this, and what is this input? This is nothing but b. So this is nothing but b, right? And finally we try to find the output of this purple OR gate. This is an OR gate, so I can write it here. OR gate will be the first input, which is a b bar. First input is a b bar plus second input. This is an OR gate, so plus symbol becomes second input is nothing but this a b bar b. Now we have seen a couple of slides back that b bar b will be 0, so this term gets dropped. So the final answer would be q equal to a times b bar. Straightforward. Now let's go to the fourth term now. And now the output of this top gate, the NOT gate, will simply be a bar, because a is the input. And if you want to find the output q, this will be nothing but the first input, which is a bar. This is an OR gate plus the second input, which is nothing but b. So we found out q equal to a bar plus b. And now we can apply De Morgan's law here. So De Morgan's law goes something like this, that xy whole bar equal to x bar plus y bar, right? So if I replace x as a, so if I do x can be written as a, while y bar can be written as b. Now you can see this takes this form, right? A bar plus b. So this I can write then xy whole bar. So the value of x is a. Clearly see that the value of x is a. So this will come out to be a, and then this is nothing but the value of y is, so y bar is b. So if you take bar again, so y bar whole bar will be equal to b bar, and then y will come out to be simply b bar. So I'll put y value is b bar, so a b bar whole bar. So this is the value of q that I am getting, right? So now we have solved all the four circuits. Now let's just go back to see what are the values that we obtained. So first we obtained a b bar, then again a b bar, then a b bar, and finally a b bar whole bar. So I'll write it here. So this is a b bar, this is also a b bar, this is also a b bar, while the output here is a b bar whole bar. So you can clearly see the first three outputs are the same, while the fourth one is different. So this will be answer, because we were trying to find the option that is the different. So fourth option is different, and that will be our answer. Thank Okay, so we are done with the first problem. If you have any comments or questions, please go ahead. Feel free to ask. This was a straightforward problem where we just solve. These are called combinatorial circuits, by the way, because so this is the combination because we are using different combinations of logic gates. So yeah, that's it. If you have any comments, any questions, or we can go ahead. The video was audible as well as visible, right? Because last time, one of the last times I did, the video was the voice was there, but the visual was not there. Both of them were there, audio as well as video, visual.
Yes, sir.
Okay.
Yes,
Okay.
sir.
Okay. So if you have, if there are no comments, I'll move ahead to the next question.
Sure, sir.
Okay. So this is the second problem now, from 2011. Let's just go ahead and I'll again play the video and we'll see. The problem statement from GATE Physics 2011 reads as follows. The following Boolean expression y equal to, and this is a big expression which I'm not going to read, but you can see on your screens. This Boolean expression can be simplified to. There are 4 options. This is a multiple choice question with 1 correct answer, and we need to find the correct one. So we just need to simplify this expression. Before we go ahead, let's talk a bit about the Boolean algebra. So Boolean algebra, we have 3 primary operations. The conjunction, which is often denoted by the AND gate, disjunction, which is often denoted by OR gate, and negation, which is often denoted by NOT gate, or this is sometimes also called as inverter, right? And we know there are only two values here, 0 and 1. 0 usually means low, 1 means high, and then depending, usually that's how it's taken. And the things that are the rules that are dictating are these are called De Morgan's laws. So for instance, you can, if using the first De Morgan law, you can convert. So you can see on the left side you have a conjunction. This dot means conjunction. On the right side you have a disjunction. So you can try to convert a disjunction into a conjunction and so on. And converse is also true. So here it's on the left side you have a disjunction with obviously a negation over it, and you can convert it in the form to a disjunction using the second De Morgan law. Right. Now we'll come back to our problem, which you can see on your screens now. So first I'll do is that now we'll try to find the terms which have quite a bit in common. So let's say if you see this term and this term, right? So what I'll do is that I can take out A bar, C and D common. So what will be left with? B plus B bar. Right, so we'll be left only with this. Now there's an interesting thing. So let's call this B plus B bar as something called X. So X is B plus B bar, and let's try to make a truth table for X. So input is B, the other input you can simply say B bar, and the output is simply X, right? So when B, there are only 2 possible inputs. B can be 0 or 1. Similarly, B bar can be correspondingly 1 and 0, and X equal to B plus B bar. So it will be 0 plus 1. It will come out to be 1, and 1 plus 0, it will also come out to be 1. Now this is also known as tautology, that this X will always be high irrespective of the value of B. So I can simply write this as A bar CD times 1, which is nothing but A bar CD. So that's what we have obtained for these 2 terms. The output simply has come out to be A bar C into D. Okay. Now let's try to find some other terms. Let me change my pen for a minute. Right, so now let's just take this term and this term, the 2 terms in purple, right? So from the 2 terms in purple, what I'll do is that I can take out A, B bar and C bar common. So I'm writing it here, A, B bar, C bar. What's left? It's D bar plus D, because I've taken A, B bar, C bar common. Right, again we just saw that any logic value plus its negation will always turn out to be 1. So I can again simply write A, B bar, C bar dot 1. This will come out to be A, B bar, C bar. Now what we'll do now is we'll try to solve the other 2 terms, sorry, which are left, which are here, right? So if I try to see these 2 terms, so I can take out A bar, C bar and D common. What I'll get is B plus B bar, and B plus E bar we again saw will come out to be 1. This comes out to be a bar c bar d. Now let me let me switch my pen again. So now what I have obtained, y equal to, so these two purple terms came out to be this, so it will be a b bar c bar plus the green term which is a bar c bar d plus the red term which is a bar c d. Okay, now what I can do is, so there is still more common to be taken, right? From these last two terms we can take out a bar d common. It will be c bar plus c. Again c bar plus c will be 1 due to the logic, the truth table that we had talked about here. This will come out to be a bar b bar c bar plus a bar d times 1. So this will come out to be, this is multiply, sorry, this come out to be a b bar c bar plus a bar d. So this is the final expression that we have arrived at. Now we saw a b bar c bar, so I'll write it here. So y came out to be a b bar c bar plus a bar d. So let's see if there are some options. So a b bar c bar, so so c a b bar c bar plus a bar d. So this is the expression that we have arrived at. So c will be our correct answer. So we're done with the problem. I wanted to emphasize one more thing. Sometimes it's not possible to take out the common. Here we were lucky that all the three terms were like b plus b bar or c plus t bar, which came out to be unity. There are some other approaches of solving this problem which are using the k maps, right? So but here in this problem, in this illustration, I was just emphasizing that just by using the Boolean algebra you can solve it. So there are different methods of approaching a problem. This is just one of the methods. So it's up to your comfort level that how you want to solve these problems. So this is just one of the approaches. All right. For people who are coming late, this is my email ID and my YouTube channel. YouTube channel is for if you are interested in some other videos, especially special electronics and special theory relativity, because I'll not be able to cover every topic related to electronics in today's and the subsequent two lectures in the two sessions. So that's that. So now I'm done with the problem of logic gate. So if you have any comments or questions, please go ahead. It's a good time to pause and reflect. So I'll wait for you people to give me a heads up. Yes, Harish, go ahead.
सर के मैपिंग से सर्किट सॉल्व करना बता दो.
What I'll do is let's just finish these problems, okay, which I have already, because the thing is, usually what I've seen is that at least in gate, K-maps is not, I mean, you need not necessarily use K-maps, because K-maps require a lot of time to draw, and there are chances of error, because if there is a then I have to establish the concept sum of products and products of sum. So what I'll try to do is that maybe in some next class, if we have some time remaining, then I'll try to cover it, the K-maps. We do not have any questions, so I'll not be able to solve the questions, but at least the understanding of the there's some beeping sound coming from one of you. Please mute yourself. Yeah, thank you. So I'll try to cover in the next class because I have to establish some concepts, and that will take time, but I'll try to cover in the next class, or maybe the next one. Okay, so yeah, any other comments or doubts regarding this problem of logic gates or Boolean algebra? Okay, I'll take that as a no, and now we'll move forward and we'll try to solve one of the fairly repeated problem, which is of ADC and DAC. These are the topics in themselves are quite complex, but when it comes down to problems asked in gate exam, they're fairly simple. They always revolve around, there are two or three kinds of problems. So first is they revolve around resolution. That we'll see what the resolution concept is. So this question also talks about resolution, by the way, you can see on the screens. So we'll see that, and the other question which talks about is the maximum time taken for conversion of this ADC or DAC, that is digital to analog converter or analog to digital converter. Only two flavors are asked. These are very straightforward problems. even if you do not understand the nitty-gritties of the circuits, which can be, I understand from physics background, it can be quite challenging, but the formula are fairly simple, because resolution is a field which you encounter in microscopy, also in optical microscopy, electron, you understand the concept of resolution. So hence I took this problem. So these are problems which you can easily understand, and with just one very let's go ahead with the video, and we'll talk a bit more about it after we watch the video. So I'm going to play the video now. The problem statement from GATE Physics 2010 reads as follows. The voltage resolution of a 12-bit digital to analog converter whose output varies from minus 10 volts to plus 10 volts is approximately, this is a multiple choice question. We have been given 4 options, and only we have to find the correct one. Only one option is correct, by the way. Right. Since the question talks about resolution, let's pause a bit and we establish some basics of resolution. So in digital to analog conversion, what do we mean by resolution? So we have a digital input and an analog output, as the name suggests, right? And so these are the two digital inputs. There will be a minimum value, there will be maximum value. Correspondingly, there will be a minimum output and maximum output. Now we know for digital input, the minimum input can be 0, and the maximum output for an n-bit digital input can be 2 raised to the power n minus 1. And so the range will be 2 raised to the power n minus 1, right? The maximum minus minimum. Similarly, on the analog side, there will be some corresponding voltage Vmin, and there will be some corresponding voltage Vmax, and their difference would be Vmax minus Vmin. Now please note that we are simply doing a mapping from digital input to analog output. We are not creating, we are not putting any power, we are not changing the value, we are just representing in a different way. So the difference between maximum and min on input side should be equal to the difference between max and min on the output side. Hence this 2 raised to the power n minus 1 should be equal to Vmax minus Vmin. So what is a resolution? Now resolution can be defined the minimum value that can be distinctly measured. The keyword is distinctly. So below this you cannot measure it accurately, right? So that means that clearly means that this means a jump of 1 bit, right? So let's say its value was something 0001. So next would be 0010. This is a jump of 1 bit, right? Because 1 when you add, it becomes 101. When you add 1, it becomes 10. So this is the minimum. This is the minimum jump that the input can afford, from green to purple. Correspondingly, the analog output will also jump from green to purple. So this is the minimum resolution, which is defined by the 1 bit change. And since we know 2 raised to the power n minus 1 steps are equal to Vmax minus Vmin, which we established here, using the unitary method, we can simply say 1 step equal to Vmax minus Vmin over 2 raised to the power n minus 1. And note that this is our definition of a resolution. Resolution is the 1 bit change. So resolution would be simply equal to 1 step, which is Vmax minus Vmin over 2 raised to the power n minus 1. Now, coming back to our problem. So coming back to our raised to the power n minus 1. I'll pause a bit here. If you have any comments, please speak, because this is the only thing of value over in this question, and even in the next question. So it's important. I just wanted to re-emphasize.
Can you explain a little?
Sorry? Can you repeat? Hello? Am I audible?
Sir, can you explain it a little bit?
So that's what I was coming to. Yeah, because it might get sometimes. So what's happening is that this is the digital to analog conversion. So we have a digital input and an analog output. And note that these maximum and minimum inputs are not under our control, so to speak. Okay, these are already predefined by the problem itself. So we have a minimum input. Digital can be 0. The maximum, if it's an n-bit input, it will be 2 raised to the power n minus 1. That's the maximum input that we can afford. Similarly, on analog side, this will be in some voltage, 2.3 volts, minus 0.6 volts, and whatever. So there will be a minimum and there will be a maximum. Now the ranges should match exactly, because note that we are not like it's not an amplifier that you give 1 volts here and you get 5 volts here. No, it's not going to happen. If it's 1 volts, it will also be 1 volts here. The format is changing. Here we are expressing it digitally. Here we are expressing in units of volts. So what that means is that the range, the difference between minimum and maximum minimum, which is 2 raised to the power n minus 1, should be exactly equal to the value of the range, which is Vx minus Vmin over this here. and the resolution is the minimum step that you can measure. For instance, a human eye cannot see the nanoscale features, right? We cannot distinguish that, right? So our resolution of eye is not that much. I think it's a 10 or 50, I forget, or a few hundred microns is the width of approximately the width of human hair, right? We cannot go below that. We will not be able to distinguish an object from other. Similarly, how do you distinguish one digital input from another? When at least one bit changes. The minimum one bit has to change, and then only you will be able to differentiate, then only you will be able to distinguish. So I assume that, let's say, whatever the MSBs are, the LSBs are 0 1. So the next jump would be 0 1 to 1 0, because that's the way it works. So 0 0 0 1 1 0 1 1, it's in binary. So this is 0 1 2 and 3. So I just took it as an example. So green is your so when the input jumps from green to purple, correspondingly the output will also jump from green to purple, and this is the change that we can measure, because this is the least thing that we can do is change one bit. We cannot change half a bit. We can change 2 bits, but the best resolution is the lower the resolution, the better it is, the better the quality. So we want a lower resolution, so only 1 bit jump is sufficient for us. That's what I have written. Resolution is minimum value that can be distinctly measured, which is the change in 1 bit, and this is then simply 2 to the power n minus 1 equal to vx minus vmin, and I simply applied the unitary method. So one step will be vmx minus vmin over 2 raised to the power n minus 1. So that's what the resolution, the whole concept of resolution is all about. Okay. Anything else you want me to, any specific point you want me to repeat?
Sir, please repeat one time.
Which thing to repeat? Because I have done it already twice. So you have to point me that, okay, this point I'm not getting. Which
two raised to power n minus step.
Okay. So Harish is saying that how did I get this number 2 raised to the power n minus 1? Okay, so let's say, so whenever there are n bit input, when the input is n bits, or when entity is n bits, the minimum value is 0 and the maximum is 2 raised to the power n minus 1. Let's take this for an example. Now these are the 2-bit numbers that you can see here. Sorry. Okay, I'll solve here. So 0 0 for n equal to 2, let's say if it's 2 bits, right? So the numbers possible are 0 0 0 1 1 0 1 1. These are the only possible numbers. These are binary representation. In decimal, this will come out to be 0 1 2 and 3. Okay, I can write it as, the good way of writing is that so this can be written as 2 raised to the power 2 minus 1. I'm noting it, writing in form of 2 ki power n minus 1. If it were 3 bits, okay, that's the case of n equal to 3 bits. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and finally 1 1 1. This is binary representation. In decimal, the representation would be 0 1 2 3 4 5 6 and 7. So this corresponds to 0, the minimum value. This corresponds to 2 raised to the power 3 minus 1, 2 raised to the power n minus 1. Note the value of n I have taken as 3. So that's how the problem statement from GATE Physics 2010 reads as follows. The voltage resolution of a maximum value or something on 0 1, the V is our definition of a resolution. Resolution is the, so that's how this 2 raised to the power n minus 1 came. Okay, because we have n bits here. So since there are n bits, the maximum value can be 2 raised to the power n minus 1, and the rest is just the difference. So this 2 raised to the power n minus 1 comes because 2 raised to the power n maximum minus minimum, like we did on the right hand side, maximum minus minimum. So that's how this 2 raised to the power n minus 1 comes. Okay, is it good now? Hello, am I audible?
Yes, sir.
Okay. So that's how we measure the resolution. Now we'll go ahead and just solve the problem. 1 bit change. So resolution would be simply equal to one step, which is Vmax minus Vmin over 2 raised to the power n minus 1. Now, coming back to our problem, so we were given a DAC with 12-bit digital, with 12-bit input, right? And the range of output was -10 to +10. So what I'll do, I'll simply write this formula which we saw in the last slide. So we know that Vmax is given as 10 volts minus Vmin is given as minus 10 volts minus 10 divided by 2 raised to the power n. N is given as 12. There are 12 bits minus 1, right? So numerator will come out to be 20 divided by 2 raised to the 12. So 2 raised to the 12. I can say 10 divided by 2 raised to the 11, right? So I can also write it as 5 divided by 2 raised to the power 10. Note that I have dropped this minus 1 terms because question says approximately. So you can afford to drop, but you cannot drop it when it's 2 ki power 2 minus 1. Then it creates a difference. But 2 ki power 12 is like 4096. So we can afford, you subtract 1 from 4096, it won't matter much. But for when n is high, only then you can drop this term. Okay, be careful. Why I do this? Because I know 2 raised to the power 10 is 1024. It's a good thing to remember, right? And I can round it off to, let's say, 1000, right? So I can say 5, approximately 5 over 1000, which is approximately 5 millivolts. So you see, I completely I did not even need to use the calculator. So which is good, because when you use calculator, the chances of error increases. But anyways, so we found the answer as 5 millivolts. So here we have B is the correct answer. Okay, so we have solved this problem now, the past problem, this one. So the next problem, what I'll do is I'll also, okay, just I'll pause again. Yes, if you have any doubts or comments, please speak, because it's important, because next problem uses the concept of this. The next problem, this problem, more or less the same. This is DAC, that is ADC. So I mean, conceptually we are only interested in resolution, so that remains the same, but I just need to I'm emphasizing it again. If there is some doubt remaining, please speak. We have time. All right, I'll go ahead then. So this is the final problem for today, and let me play the video. The problem statement from GATE Physics 2014 reads as follows. In order to measure a maximum of 1 volts with a resolution of 1 millivolts using an n-bit analog to digital converter, working under the principle of ladder network, the minimum value of n is. So in this problem, so what we are given is that we have to use an n-bit A to D converter. So this is a black box, let's say. So this is an A to D converter, analog to digital converter. So on this side, you will have an analog input. It can be anything, right? So voltage, let's say, right? And it will have a digital output, right? So I can denote it something like this. So there are n number of bits. So this is the 0th bit, and there will be the first bit, and then there will be correspondingly there will be the nth bit, and all of these bits have some corresponding 0 and 1. So the maximum range that we can achieve is, this will be 0 and this will be 2 raised to the power n minus 1, right? These are, so this will be the decimal value that we can achieve, 2 raised to the power n minus 1 on the output side, by the way. Okay, and so maximum value that so in order to measure a maximum value of maximum of 1 volt, so we are given that the maximum that this can reach is 1 volt. So Vmax is given as 1 volts, and the resolution of this A to D converter is 1 millivolts. So resolution is 1 millivolts. It's an n-bit converter, and using the principle of ladder network, we'll see in a minute that you see how to implement this ADC. There are different architectures. So there is ladder network, there's a dual slope, there are various other architectures. So what what we'll see is the ladder network, which is a fairly simple to understand, to visualize. So we'll see that in the next slide, and we need to find the value of n. So that's the problem. But first let's have a look at the by the way, this ladder network ADC is also known as flash ADC. So flash ADC implements the ladder network, right? So what we have is, so as we saw that on the output side there will be a Vmin, right? So this will be corresponding to, let's say, 0, and on the and correspondingly this is to 2 to the power n minus 1. This is the decimal value, by the way, for the binary number. And correspondingly on the input side, there will be Vmin and Vmax, right? So So these are the input side, the analog values, right? And so analog value will be fluctuating, like can be anything, but in between something like this, right? So what's going to happen is that, so let's say at this point of time I need to find what is the digital value, or let's say at this point of time. So how do we find that? What we do is that we create some references. Okay, so we create some references. So this is the minimum. We cannot go below the minimum, you cannot go above the maximum. However, in between you create many reference values. So let's say you have so corresponding to this, let's say we are somewhere here, right? So what will it say is that it will compare the analog value, this is the analog value, V analog. It will compare the analog value to the reference value. So you can see the analog value is greater than Vref2, right? So this will assign it. So this will be corresponding to the value 1, and this will be corresponding to 2, right? When you convert it in the decimal, this binary will come out to be 2. Similarly, we can say it's, since it's the cross Vref2, so we assign it the value of 1 0 in binary code. This is the decimal code. This corresponds to 0 1 0 0 and so on, right? And let's say if it's here just above this, then since it's crossed the yellow line, so it will be corresponding to 3. So this will be 1 1 1. This is the binary 1 1, and there will be preceding zeros. So correspondingly, what we need to do is that for every sample of the analog value, we'll compare to this some reference voltages and accordingly assign a digital value to that. But first we need to create all these reference values, and the way to create these reference values is to something called use the ladder network. So on the left of your screen, you can see the ladder network, extreme left, this region, right? You can see, so there is some reference which is usually 0 volts, right? So in this case it's 0 volts, and there is a high which is 1 volts. Okay, and in between you will find many reference voltages, 2 raised to the power n minus 1, n minus 2, you can see correspondingly, and green is 2 raised to the power n minus 3, which is here, and Vref1, Vref2, and so on. So this ladder network, just the higher you in the ladder network, higher voltages, higher reference voltages you will see. And once we have all these reference voltages, now we'll simply use a comparator using an operational amplifier, and we'll compare the input voltage to this comparator. So some of them will go high, and correspondingly will output this this digital output. This is what typically happens in a thermometer. So because you see, when you measure the body temperature or even the atmospheric temperature, so this is the circuitry behind a digital thermometer. So that's what's happening. Yeah. Anyway, so the question talked about resolution, and let's see the resolution quickly. So this is analog to digital conversion, and now again in this video also I'm going to talk about the resolution again. So if you have any doubts, just try to be attentive, and just so that some of doubts may get cleared again. Correspondingly, we have a analog input and digital output. There's a minimum value of an analog value, and there's a maximum value, and so correspondingly there will be a minimum output and maximum output, and we are denoting this on the analog side as Vmin and Vmax, and so the difference will be Vmax minus Vmin. Correspondingly, the minimum output can be 0 in digital, and the maximum output can be 2 raised to the power n minus 1. This is in binary, and encoded as decimal, right? So note that we are not creating any voltage. We are not providing it. So there is no amplification or attenuation. So the thing on your left should exactly map the thing on the right. So input should exactly map the output. This means Vmax minus Vmin should be exactly equal to 2 raised to the power n minus 1. And what is the resolution? Resolution is the minimum value that can be distinctly measured. So what we mean by that, this 1 bit change. So let's say the value here was something 0 0 1 0. These are the LSBs, and so correspondingly 1 bit change would be 0 0 1 1. Only 1 bit change, right? And this is the resolution. So if you can measure, then that will be the resolution, because output is digital. Okay, so since there are 2 raised to the power n minus steps, which corresponds to Vmax minus Vmin, by simply applying the unitary method, you can see 1 step equal to Vmax minus Vmin over 2 raised to the power n minus 1, and we know that this 1 bit change is nothing but the resolution, or the minimum value that can be distinctly measured. So that will be Vmax minus Vmin over 2 raised to the power n minus 1. Right. So getting back to our problem, this is the resolution formula that we derived. So resolution is given in the problem is 1 millivolts, right? Vmax minus Vmin. So Vmax is 1 volt. This is given. The question is silent about Vmin, but we'll assume it to be 0 because usually it's ground, and even if it's not given, we'll assume it to be 0. So 1 minus 0 over 2 raised to the power n minus 1, right? So I'll take 2 raised to the power n minus 1 to the left side. So this will be 1 over 1 millivolts. So this will give 2 raised to the power n minus 1 should be equal to 1000. This implies 2 raised to the power n should be equal to 1001. Now, there are two ways of doing it. You can take the log and you can just do the calculator, and if you solve this, n will come out to be something 9 point something. Okay, now we cannot have 9 point something, so we can, n is an integer, so n can be 9 or 10 or 11 or 8 maybe. So what the question asks minimum value of n. So if the n were 9, if you take n equal to 9, then you cannot achieve this resolution, because remember that will be 2 raised to the power 9 minus 1, right? So this will come out to be very close to 0.5 millivolts. But if we use n equal to 10, let's try to solve it. So let's try to find this formula. So for n equal to 10, I'll change the pen color so that you can clearly understand. So for n equal to 10, R10 I'm noting it as, so it will be 1 minus 0 over 2 raised to the power 10 minus 1. So this will be 1 over 2 raised to the power 10. 2 raised to the power 10 is approximately 1024, but if I approximate it to 1000, right? So this will come out to be approximately 1 millivolts. So when n equal to 10, the resolution is 1 millivolts, which clearly matches. However, if you were to do, let's say, n equal to 9, which I'm solving it here. So let's try to find out R9. So this will be 1 minus 0 over 2 raised to the power 9 minus 1. This will be 1 over around 511 actually. So if it's around 511, this will approximately come out to be around 2 millivolts. Almost double that. But we need the resolution of 1 millivolts. The lower the resolution, the better. And in order to achieve a resolution of around 1 millivolts, we must use 10. We can use higher also. If let's say if we use 11, so this will again go to 0.5 millivolts. If we use n equal to 12, this will go to 0.25 millivolts. There's scaling of factor of 2. But we need around 1 millivolts, so we'll put n equal to 10, and hence, so our answer here would be the value of n is 10. Right. So we are done with the problems. If you have any doubts now, regarding the flash ADC, just you need not go into the circuitry, how is it comparing. That's for electrical engineering people. That's not for you. But the idea of resolution has to be there, because that is something very core to physics, right? And even for electrical engineering also, for every discipline for that matter. But the whole point of these two the problems for ADC and DAC is to emphasize that it's just the resolution is the thing, that even if you prepare for resolution, which is just one formula and very simple mapping from input to output, the questions can be solved relatively easily. So that was my aim by solving these two problems. So we are on time. The session is complete from my side. If you have any doubts regarding the digital electronics first, you are welcome to speak. If you don't have any doubt of digital electronics, then I'll wait still because you might have doubts from some previous topics and whatnot. So thank you for your patience. If you have, yeah, Harish, go ahead.
मुझे
I'm not able to hear you, Harish. Just if possible, can you type?
Hello.
Yeah, go ahead.
Sir, special theory of relativity में doubt है.
So we'll wait for that. Let's let other people say. You're welcome, Amit. Ohidul, yes. So I did talk about Harish. We'll talk about special theory of relativity once we are done with digital electronics. Okay, so I request you to stay back a bit. So Ohidul, yes, concepts. Yeah, time taken for conversion. Yes, I had mentioned it. The thing is that I already solved this problem in my one of my previous videos, which are on this channel. I forget the video. I mean, which video it is. I'm sorry about that, but you can go to this channel and just try to find out. It's in one of the videos of digital electronics. I think the last video of digital electronics. Just please go ahead.
Okay, sir.
Yeah. Okay. Thank you.
Thank you.
Yeah. Okay. Yeah. Any doubts on digital electronics? Please go ahead. All right. If no, then this session closes for digital electronics. Harish has a doubt on special theory relativity, so I'll stay back for that. You're welcome to leave. You're welcome to stay. It's your choice. But digital electronics part is over unless any one of you has a doubt. So this is the all right. So thank you for your patience. Thank you for your time. Harish, go ahead with a doubt on STR.
सर ये न्यूटन एक गेट का क्वेश्चन है न्यूटन का जो सेकंड स्पेशल थ्योरी ऑफ रिलेटिविटी में कैसे लिखते हैं सर वो नहीं लिख पाया
Okay, so Harish is asking how to write Newton's law in special theory relativity. Um, how should I say this? Okay, so we had talked about initially, if you remember, we started about only x and t, the position and time, and we talked about Lorentz transformation. And then how the Lorentz transformation links between the frame x and s prime, so we can derive x prime if we know x and so on, right? And then based on this concept we derived something called velocities, right? So we can derive the velocities because velocity is delta x over delta t. Now the whole thing in that understanding was that the frames we were took were inertial. So now when you are applying force, so there have to be some changes have to be made in the analysis itself, because the frames when you are applying a force F equal to ma, so the force in one frame may not be the same as force in the other frame. So the concept of inertial frame, which was at least which I was focusing on, right, based on the syllabus, so that picture gets distorted. It's not that all the concepts are irrelevant now. It's just that the acceleration part is also there, so all the equations of motion will need to correspondingly change, because the energy, see, the only thing we know is that energy must remain conserved, right? When you are applying a force, so there's a work done F dot integral F dot ds closed loop, right? So those things, so that energy is also, I don't know, to be honest, I don't know how exactly will it be mapped. So I don't know, I'll have to look it up, and then only I can email me the problem and your solution, your approach, and then we can discuss it. Okay.
श्योर सर
Okay, good. Yeah. Anything else?
तो सर मॉक टेस्ट का रिजल्ट कब आएगा जैसे आज मॉक टेस्ट हुआ था
Okay, so Harish is asking about the result of mock test. Unfortunately, I'm not aware of the administrative side of it. The only thing I can suggest you is just write them an email saying that when will the results be declared. Because someone was also mentioning that there are some answers may be wrong. So unfortunately, I do not have any idea about the results of mock tests and their grading, how they're normalizing and whatnot. So I can't help you on that. Sorry. Just write an email to them. They're usually very responsive. So it's not like there'll not be any undue delays. And that much I can promise. Yeah.
Excuse me, sir.
Good
Just
evening.
can you please once say how to go login for mock test?
Your can you be louder, please? It's not very, its intensity is low. Can you please be louder?
Sir, I have joined late, so
Okay.
I missed that mock test part that you have suggested. Can you please repeat that?
Okay. So just hold on a second. Let me share my presentation again. Okay, just give me a minute. All right. You should be able to see in your screen, right? My presentation.
Yes, sir.
Huh. So every Sunday 2 to 5 p.m. NPTEL is conducting a mock test. You have to go to, you can see on your top the website gate.nptel.ac.in. In that, if you go to this tab, there you can join you have to register obviously, and then only after you will be able to join the mock tests. If This is the way, other people can correct me if I'm wrong, but I believe I am not registered, by the way. I'm just following the flow. I think this is the way. So you can just try that. It's good. The more mock tests you give, the better your command becomes, because sometimes it becomes a trouble just for sitting for 3 hours. That in itself becomes a challenge on some days. If you, especially if you are from northern India, where it's biting cold, you are habitual of sitting in a blanket while reading. In the exam hall, there'll be no blankets. It will be biting cold. So those things also matter. So you have to have that discipline and prepare yourself for the sitting for 3 hours. That's important. You have the mental capacity and the physical capacity. So it's a good thing to practice. Yeah, I strongly advise you to go give these mock tests. If you are attending, if you are writing any other mock test, please do that and monitor your progress. Keep on improving. So that's it.
We have to go for mock test progress option or a go to course option.
Okay, somebody else have to tell me that. Harish, you have given the test, right? What's the process?
यस सर सर पहले हमें एक रजिस्ट्रेशन फॉर्म फिल करना पड़ेगा
So Harish is saying you have to fill a registration form. Where is that form, Harish? Which
सर
page?
इसी
Huh?
सर आप अभी गेट प्रोग्रेस टेस्ट है ना यहाँ पे जाके
Mock test progress, you mean to say? If I click this, then
गो टू कोर्स
okay. So
इधर ऊपर
हाँ ठीक है, it's fine. I'm not open. The website is not open. I'll try to open this. Okay, just hold on a second. Let me try to open it. nptel.gate.nic.in. So again, it asks me to register. So it remains the same. So you have to click on. Okay, I'm sorry, I'm lost. So you have to click on this option. Rather than mock test progress, click on go to course, and there you'll get some option. But you have to register.
गो कोर्स ये सर
So we go to course, and then there's an option for registration. That's what you're saying, right?
Yes, sir. Go to course.
So I request, if you are interested in giving the mock test, and I strongly encourage you to just, instead of mock test progress, click on go to course. But again, you'll have to register. So that
Yes, sir. Go to course.
So that thing remains the same. So that's it.
Sir, after going the go to course, there is many subjects like physics, chemistry. We have to choose a physics subject.
Okay.
Then they will ask some general details,
Okay.
and submit the form.
Okay. So that's the progress. That's the steps that you have to follow. It's fine. It's good. It's good. You should try the mock tests. All right. So yeah, that's that. Anything else?
No, sir. Thank you.
Okay, you're welcome.
Thank you.
Okay, I hope you write the test Galaxy A21s. Okay. Okay. Thank you, everyone. If you have no more comments or questions, we'll close this session. Thank you for your patience. Thank you for your time. Stay safe. Good night. Goodbye.